In this video, we will discuss how to convert epsilon NFA to DFA directly. In previous three videos, we have discussed various examples of converting epsilon NFA to NFA. In this video, we will directly convert it into DFA. This is the epsilon NFA that we want to convert into DFA. Let us first understand the algorithm for the conversion. We need to compute epsilon closure of initial state Q0. Let's call it Q, and we will add that Q into one list. Let's call it as a L. Now one by one we will compute delta transition function, and then we'll compute epsilon closure of that for every state in L. So while for all Q, if Q is in L and if it is not processed, then we have to repeat this. If that state is processed, then we don't have to explore it. So initially it is just epsilon closure of Q0 which is not processed. So we have to apply following steps on that. And if new states are generated, we will be adding into L, and we have to keep iterating that process until all the states in L are processed. For each input symbol, AK belongs to sigma, do following. So this process we have to repeat for all the input alphabets A, B, C or 0, 1, whatever we have. Compute P as follow. P is equal to epsilon closure of delta transition function of Q on input alphabet AK. If this P is not already processed, then we have to add it into the list. Okay, so we'll add P to the list. If it is processed, then it is already in list. So no need to add it into list again and again. And this process we have to repeat for all the states into the list. Once all the states are processed, now then we will go to construct the DFA of generated states. Let us understand it through example. So this is our epsilon NFA, and first step is to compute the epsilon closure of initial state. Here we don't need to compute it for all the states. We will just compute it for the initial state. Let us call it as a Q, and this Q we will be adding into the list L. Now for one by one, we will be selecting one by one unprocessed states from list, and we will be computing epsilon closure of delta function of Q. So we'll find the successors of epsilon closure of initial state, which is nothing but epsilon closure of delta Q0, Q1, Q2 on input 0. So that is given by epsilon closure of union of all these three states on input 0. So delta Q0, 0, union delta Q1, 0, union delta Q2, 0. From transition diagram, we can see that for input 0, there is only transition present from state Q0, which remains on Q0. For Q1 and Q2, there is no transition for input 0, so that would be 5. And ultimately, that will lead us to epsilon closure of Q0, which is nothing but state Q0, Q1, Q2. See, this is the same state we started to process, right? This is what our Q, initial Q in list. So we will not add it again into the list. It is already there, and now it is being processed. So for input alphabet 0 we have processed. Now we will process it for input alphabet 1. So again, for the epsilon closure of initial state, we have to find out successor for input 1. So that is given by epsilon closure of delta Q0, Q1, Q2, comma 1. So again, we need to take union of all these three delta transition for input 1. There is only one transition available for input 1, that is from state Q1. So we have a 0, union Q1, union phi, and ultimately we have to compute epsilon closure of Q1. And epsilon closure of Q1 is nothing but it's a Q1 and Q2, because every state is epsilon closure of itself. And from Q1 we can move to Q2 by consuming epsilon symbol. So that will also be into the epsilon closure of state Q1. So we have Q1, Q2. Now Q1, Q2 is a new state. It is not processed. It is a new substate. So we have transition diagram like this, and this is our Q. Q0, Q1, Q2 was initially added. Now Q1, Q2 is also added into this list. And now we'll compute the successors for input symbol 2. Okay. So that is epsilon closure of delta Q0, Q1, Q2, comma 2. Again, we will take the union of delta transition function for all these three states Q1, Q0, Q2. And from transition diagram, we can see that only transition for input alphabet 2 is available from state Q2, which remains on same state. So that is phi union Q2, and ultimately it is epsilon closure of Q2. And epsilon closure of Q2 is Q2 itself. Again, it is a new subset. So that we need to push into the Q. So this is our Q now. For all three inputs, we have processed the epsilon closure of Q0. So Q0, Q1, Q2, we have already processed. We have two new subsets, Q1, Q2 and Q2, so which are shown in red color, and gray means it is already processed. Now we have to repeat we have to compute the delta transition functions for Q0, Q1 and Q2. In any order we can go. Either first we can explore Q1, Q2 and then Q2, or vice versa. Order does not matter. Just we need to explore all the states in the list. That's it. So let us try to compute successor of Q1, Q2. So that is epsilon closure of delta Q1, Q2 on input 0. So epsilon closure on input 0 is given by union of these two delta transition functions, and there is no transition function from Q1 or Q2 on input 0, so that will remain phi, and epsilon closure of phi is phi. Next we'll compute it for input 1, and for input 1 we have to take the union of these two delta transition function, and there is an arc from state Q1 on input 1 which remains on same state, so that will be Q1, and there is no arc from state Q2 or no transition from state Q2 on input 1, so that will remain phi, and union of Q1 and phi would be Q1 only, and the epsilon closure of Q1 is Q1 and Q2. So that is the final answer, and now we will compute it for the input alphabet 2. So that will give us Q2 only. So the state Q1, Q2 is also processed, and there is no new state is created out of it, and because Q2 is already there, so we don't need to push it again. And finally our Q would look like this. Q1, Q2 is also processed, and Q2 is remaining now. So now we will repeat the same process for state Q2. So we will compute the successor of Q2 on input alphabet 0, which will remain phi. For input 1 also, that would be phi because there is no transition, and for input 2 we have one transition, it is in same state. Fine. So epsilon closure of Q2 is Q2 itself, so that will be the output, and if we add the row into the transition table, that would look like this: Q2 phi phi Q2, and all three states are converted into gray. That means now there is no new state left. We have already processed all the states. Whatever transition table we have on left, it is for the DFA. So now we will draw the DFA for that. So either we can rename this state and we can draw it, or we can draw it as it is. So if you think that it is difficult to draw DFA for longer set of states, then we can replace Q0, Q1, Q2 by A, then Q1, Q2 by B, Q2 by C, and then we can draw DFA for states A, B, C, etc. That's okay. Whatever you prefer, you can do with that. But the transitions will not change. It will remain as it is. So this is how we can convert epsilon NFA to DFA. Thank you. That's it for today, folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.